Let's dive into some implicit differentiation. We're gonna first look at some notation, look at the basics of this thing, and then kind of dive in with a bigger relation and see what this looks like in the different types of problems that you could encounter with this thing. So you may have seen something like this in the past where you are asked to take the derivative with respect to x of x squared. And I know that that's just 2x. You may have also seen something where they give you y equals x squared, and then write that as a result, dy dx, or the derivative of y with respect to x, would be equal to 2x. So the question is then, what happens when this operator, this d dx, doesn't agree with the variable here? This is saying take the derivative of whatever's here with respect to x, but all of a sudden we have a y here. Well, if you want to sort of think about this a little bit crudely, you think about, in order to manipulate this, we need to bring in a giant 1 of dy over dy. That allows us to rewrite the way that this is written. If you think of these differentials sort of combining in fraction form, of being, well, this is really dy dx with a d dy times d dy of y squared. This means that the derivative with respect to y, these variables now agree, and now we can write that this is equal to 2y dy dx, and this dy dx is hanging around here in the back. So the derivative with respect to x of y squared equals 2y dy dx. I like to think of this dy dx as like a byproduct of taking the derivative of this y squared with respect to x when these variables don't agree. If you would have done it up here, I think about it as this x and this x agree. There's sort of like this ghost dx over dx byproduct that just is 1, and so we don't need to write this, and it's just equal to 2x. If we use another example where we have take the derivative with respect to x of x cubed plus y to the 4th, say minus 2y, we end up with a derivative that is 3x squared plus 4y cubed dy dx minus 2 dy dx. And you can see we kind of get this byproduct, so to speak, this dy dx, this differential, every time we take the derivative with respect to y. So what happens if we have a bigger relation, a bigger equation, one that is implicit, meaning x and y are on the same side of the equation versus an explicit equation that you might have seen in the past, like y equals x squared. So here's an example, and first I'm gonna take this one step at a time, and we're just gonna find dy dx. That's gonna be our first step. We're gonna do that for this whole relation. We're gonna find the derivative at any given xy point. So I'm gonna go through, notice I have a product rule that I'm gonna have to apply in the middle of this thing. So first, the derivative of 3x squared is 6x plus, and I'm gonna divide this into my two factors here, 1 d2 plus 2 d1. So again, we have 6x from the first term, then 2x times the derivative of y, which is dy dx, plus y times the derivative of 2x, which is 2, minus the derivative of y squared would be 2y dy dx, because remember, we're taking the derivative of this whole equation with respect to y, equals, and be careful because sometimes people just want to write -4 over here, but really the derivative of -4 is 0. So now I need to solve for dy dx. The best way to do this, at least in my experience, is to move all of the terms with dy dx on one side and everything without, all the terms without dy dx to the other. So I'm going to rewrite this as 2x dy dx minus 2y dy dx equals, and I'll subtract 6x over, and I'll subtract 2y over. And at this point on the left, I'm going to factor out a dy dx, leaving me with 2x minus 2y equals negative 6x minus 2y. The right side doesn't change. And now I'm going to divide both sides by 2x minus 2y, giving me dy dx equals negative 6x minus 2y over 2x minus 2y. So just like an example with an explicit function where you get a derivative that gives you the slope of the tangent line or an instantaneous rate of change at any given x value, now you have the same sort of scenario, but now your derivative is based on x and y. And this is important because if you consider this sort of graphically, if you have some relation buzzing around and you have a point here and a point here on just some random curve, this point and this point might have different tangent line slopes, but for the same x value. So the y value becomes important here to distinguish, do I want the tangent line slope at the top or at the bottom of this curve, depending on the positive or negative value for y. So that's kind of the first thing where we could find the slope of the tangent line or the derivative of this relation at any xy point. Now, you might also be asked to do this specifically at a given xy point. Let's move this just up here for now. And let's see if we can dig in a little bit deeper. So we already know that dy dx equals negative 6x minus 2y over positive 2x minus 2y. So here's our derivative, and we want to know the slope of the tangent line at, say, x equals 0. So the first thing we're going to need to do is find out what the y value is, or y values are, that match up with this x equals 0. To do that, since these are points on my curve, I'm going to go back to 3x squared plus 2xy minus y squared equals negative 4, and I'm going to substitute 0 in for x. That means I end up with 0 plus 0 minus y squared equals negative 4. So I have that y squared equals 4, which actually means I have y equals plus or minus 2. So I have two values on this relation that are actually 0, 2, and 0, negative 2, that not only fit on this curve, but now if I want to find the slope of the tangent line when x equals 0, if I want to evaluate dy dx when x equals 0, 2, I'm going to need one tangent line slope, but I'm also going to need dy dx at the point 0, negative 2. And I'm going to have to do this twice. So this just means I'm going to take dy dx and evaluate it at 0, 2, and do the same thing for 0, negative 2. I'm going to use the dy dx that I have from above, just plugging in 0 for x and 2 in this case for y. So I have negative 6 times 0 minus 2 times 2 over 2 times 0 minus 2 times 2. And if I simplify this at those 0, 0, I end up with negative 4 over negative 4, otherwise known as 1. So I get a slope of the tangent line at 1. If I wanted to go a step further, I could say y minus 2 equals 1 times x minus 0 is the slope, or is the equation of the tangent line in point slope form through the point 0, 2 on this curve. At 0, negative 2, I'm going to go through the same process. I have negative 6 times 0 minus 2 times negative 2 over 2 times 0 minus 2 times negative 2. See ya later. And I end up with positive 4 over 4. So I end up with positive 1 here too. So interestingly enough, y minus negative 2 equals 1 times x minus 0 is the equation of the tangent line at this point as well. Now, a little side note shortcut here. If the problem did not ask for dy dx, if the direction was not find dy dx, but rather straight away, this said find dy dx at 0, 2, you could actually skip some of the work that you have here. You can actually sort of bypass all of these steps and streamline your work, knowing that you really don't want dy dx at any point like you found here. What you really want is you want dy dx at the point 0, 2. So if you implicitly differentiate, you can streamline your work by putting in 0 for x and 2 for y right now. Let's see if the result is the same. 6 times 0 plus 2 times 0 dy dx plus 2 times 2 minus 2 times 2 dy dx equals 0. So if I plug this in, I get 0 plus 4 minus 4 dy dx equals 0. If I add this to both sides and divide by 4, I get dy dx is equal to 1. That's the exact result that I got when I went through it by first finding dy dx and then plugging in my value. So again, just a way to kind of streamline things if you're asked for it at a point right off the bat. Otherwise, you're going to need to go through and find dy dx by putting it on one side, dividing your extra factor over, and sort of taking your time to make sure that whatever you have here matches up, if it's a multiple choice question, or whatever else you're being asked to do at the time.